Okay, so welcome to the third and last lecture in the block on semantics or on computer science applications of proof assistance. And now the flavor of semantics that we look at is called denotational. So you can think of it as a more mathematical semantics, if you like. Or another way to think of it is as a compiler or translator. So we take the syntax and we translate it directly into the language of mathematics. It's a compiler into mathematics, if you like. And first of all, we start with a little discussion on compositionality, which is the property that we want the denotational semantics to have. It's the characteristic property in general. So denotational semantics is a function from syntax to semantics, and often we use these double brackets or clear brackets, around an expression to say this is the semantics of the expression. So that's quite common in theoretical computer science. And so here, the domain is some syntactic objects. So, for example, while programs or arithmetic expressions. And on the semantics side, you have, the value of such an object. So it could be a function, right? So programs typically denote functions or a relation. If there's non-determinism, for example, then you cannot have a function. You have to have a relation, or if you have non-termination or partiality and so on. So the general framework is always syntax to semantics, but the instantiations can be arbitrary, if you like. And then what we want is compositionality. We want the meaning of a compound statement to be defined in terms of the meaning of its components, right? So if you have an if then else and it has two branches, you want the meaning of the if then else to be defined in terms of the meaning of the then branch and the meaning of the else branch. So this is what we show here. And same thing, sequential composition. We want, on the right-hand side, we want to talk about the meanings. That's the goal. Whereas with operational semantics, it's a big spaghetti. It's like a go-to or go-to program, if you know what that means. And here we want something very clean, mathematical, where we can analyze a program, piece per piece, and look at semantics of the different pieces in isolation and combine them together. And compositionality has lots of benefits because it allows you to scale. Basically, it allows you to understand bigger programs in terms of smaller programs. It also means that we'll be able to reason equationally, so with simplifier, which we couldn't do with the other two semantics. Here's a concrete example of a denotational semantics. It's the eval function on arithmetic expressions. Do you remember when we met an operator such as plus, we would say, well, the plus of two expressions is the semantics of one, or eval of one expression plus, the leans plus the semantics or eval of the other expression, right? That was actually a denotational semantics, but it was just for expressions which have no side effects. And now we're going to do the same for a programming language that has side effects, and that also has a while loop, which may not terminate. So you see here eval instead of the funky braces here. You have arithmetic expressions, which is the syntax, and the semantics is a bit complicated here, but it says, well, it's a function that takes an environment and returns a value. Right? So normally we would not put these parentheses because they are redundant. But here I've put them just to emphasize that this is the semantics part of the definition. Okay, so now let's look at our first attempt at defining a semantics. And we're going to define a relational semantics, not a functional one. The advantage is that we don't have to have a termination or even determinism, so it's a more general setting in which we can work. So that means, you know, with a function, we'd start in a state and end up with a state. So we'd have a state arrow state. That would be our, you know, the semantics. That would be, you know, this part of the definition. But here, because we're working with relations, what we have is relations over states, right? So binary relations over states. So you relate start states or initial states to final states. And you can do that using binary predicates or using binary relations. Here we do it using binary relations. In proof assistance, the two are isomorphic. Well, actually, also in real life, not just in proof assistant. And then what we see is that for 4 of the 5 statement types, the semantics is quite easy to define. So skip is the identity relation. So let's try to find its definition. Right, it's also defined in loblib. And what we have is that basically it's a set of all ABs, right? So these are pairs, right? So letter A represents an element of type alpha and B represents another element of type alpha, and the two are paired. So we'll often use names like this for pairs, where the second component of AB equals the first component of AB, right? It would have been nice to be able to write something like this. Unfortunately, Lean doesn't parse that, so we have to write the pair and use the selectors explicitly. Okay, let's go back where we were. So skip says, well, whenever you're in a state before, you're in the same state after. Nothing happens. That's quite natural. Assign is the set of pairs of states, ST, right? Where the first state is S and second state is T, at least in our mental model. And the idea is that T should be equal to S, where you perform a little update, where you say that N is updated to be the value of A in S, right? So that's the semantics of assign. Sequential composition is easy. It's right, the denotation of S, and then composition with the denotation of T. And this is the big circle. It's not the little circle that we use for functions. It's a circle for relations. And composition of relations is left to right, unlike that of functions, which is right to left. So this really means you do S first, and then you do T. But you have to be very careful here, right? That you really write what you mean. And you know, if you don't, you have to catch it somehow presumably by proving some lemmas. Right. Then you have if then else. If then else introduces a new little operator here, the down left harpoon. So good luck typing that in. So I recommend copy paste. So the down left harpoon restricts a relation to you know, relations set of pairs, and then this checks if the first component of the pair satisfies a given predicate, which is B here, right? So it says the semantics of if then else is basically semantics of S, you know, for all pairs where the first state satisfies B, right? So basically, if B is true, then you would take the then branch, and this is the then branch, and then this is the condition that B is false, and then you take the T branch, right? We can look at the definition of that operator. Again, it's in lovelib. We're basically saying, yes, the set of all AB, right here, it's over alpha. We don't talk about states. It's a more general operator. Again, it's a set of all ABs such as P of A, and the condition is called P, not B. So P of A, and you also have that AB is in R to start with, right? So you restrict a set R. This is the, I mean, this is basically just a set R, and this is the restriction here. This is how it works, and this is the fancy syntax. Okay. Okay, so that wasn't so bad. So you can think about, I mean, can look at all the definitions. I mean, you might not have understood everything now, but if you study each definition closely and remember from the from lecture 6 about monads how sets work. So there's a bit about sets, especially in the Hitchhiker's Guide. Then you should have no problems understanding what happens here. And if you do have problems, then just ask in the Q&A. But now we have to define while, and this is where this is where sorry comes into play, right? We're a bit stuck because we'd like to define while in terms of while. You know, basically what we would like to write in the sorry is this, right? And then you know, Lean just complains that this is not well founded, possibly. And it is indeed rather worrying here. You really have this recursion, and if the program is non-terminating, if you know, if you have a while true, then in this definition also will not be terminating. So there's no hope to convince Lean that this is well founded, because it might not be. It is not well founded in general. There are counterexamples. I just gave one. So there's no hope here. I mean, this looks extremely worrying because it's exactly, you see, it's exactly the same argument that we had here. So we're not making good progress. Okay. So we'll find another trick instead. And most of the, at least much of the lecture will be dedicated to that trick. And it's somewhat mathematical in flavor, right? So it's a good preparation for the next few lectures, which will be given by my colleague Gabriel Ebner. So let's step back. What we're looking for is an x such that this equation holds, right? We're trying to define denote. I mean, we're trying to define that beast. Right, so we want to define it so that it satisfies this property, but right now it's not defined. So we want a value x that satisfies this, and this is what we'll set. You know, we'll then set this denote here to be x. Right, this is what we'll do. And what we see here is a so-called fixed point equation. I mean, because you have on one side, you have what I call a naked variable. You just have a variable and nothing else. And then you have an equality. And then you have a function of the variable on the right-hand side, right? So that's a fixed point equation. It means applying the function once has no effect, you know, on the value of the variable. And what we're going to do in most of this lecture is define an operator least fixed point, LFP, where you can give it that equation here, and it will give you the x under some conditions, right? And also what we give is not exactly the equation x equals blah, blah, blah. What we give is lambda x comma blah, blah, blah. So the syntax is a bit different. You're basically given the right-hand side and, you know, as a function of the lambdas, right? So if this here is seen as x equals f of x, what you're giving really is the f, which is also the same as lambda x f of x. You're giving this term here. This is what we see here, right? This is lambda x, and this is f of x. But we need to build this LFP, right? You know, otherwise we would not be able to fill 1 hour and a half of lecturing. Okay,